Welcome to Grade 12 Artificial Intelligence. In this module, we look at how AI research is actually done, not a single algorithm, but the method behind every honest result. Asking a sharp question, designing a fair experiment, testing for significance, and making the work reproducible. This is what separates a real finding from a lucky number. Here is our plan for the module. We'll walk the research life cycle from end to end. We'll frame a question and a hypothesis and survey what is already known. We'll design a fair experiment with datasets, baselines, ablations, and clean data splits. We'll test whether a result is statistically significant, make the work reproducible, and finish with writing, peer review, and research ethics. Every AI study moves through the same 6 stages. First, a question. Ask something worth answering. Second, a review. Read what is already known so you don't repeat solved work. Third, a hypothesis. State a clear, testable prediction. Fourth, the experiment. Design a fair, controlled test. Fifth, analyze. Measure the outcome and check it is significant, not noise. Sixth, communicate. Report it so another team can repeat it. And this is a loop, not a line. Each answer raises a sharper question and the cycle begins again. Let's take these stages one at a time. Strong research begins with a strong question. A good research question is specific, answerable, and measurable. Asking whether deeper networks read X-rays better than shallow ones is sharp. Asking whether AI is good is not. From the question we form a hypothesis, a prediction we could be wrong about. If no result could ever disprove it, it is not a scientific claim. Before running anything, we read the literature, the published work in the field, to learn what is already known and where the open gap lies. We cite that prior work and build on it rather than rediscover it by accident. With a clear question and a falsifiable hypothesis, we can design the experiment. A fair experiment is built before any model is trained. Take a Rwandan crop disease dataset of leaf photographs. We split it once, most of it for training, a slice for validation, and a held-out slice for the final test. We need a baseline, a simple, honest reference such as logistic regression, so we know what beating it really means. We tune and choose our model on the validation set only, and never touch the test set while developing. Used once at the end, the baseline scores 81% and the convolutional network 88%. Then an ablation. We remove one piece. The data augmentation and accuracy falls to 83%. That tells us how much each part actually contributed. A single number can mislead, so we ask whether the gap is real. One run is not evidence. We repeat the experiment over several random seeds and report the mean and its variation. The network averages around 88% and the baseline around 81%, each with a small spread. We report a confidence interval, a range the true value likely falls in, rather than one lucky figure. A significance test gives a p-value of 0.002. A gap this large would rarely happen by chance alone, and we check the effect size. A 6-point gain is not only significant, it is large enough to matter in practice. Significant and meaningful are two different tests, and good research passes both. A finding only counts when another team can reproduce it. So we release the code and the exact dataset or clear instructions for obtaining it. We fix the random seeds and report them, so the same run gives the same numbers. We record the versions of every library, the hardware, and all the hyperparameters we chose. We state the compute used, the hours, and the devices, because cost is part of the claim. Major venues now require a reproducibility checklist, covering code, data, compute, and statistics, before a paper is accepted. Reproducible work is what lets the whole field build forward with confidence. The last stage is writing the work up and putting it before others. A paper states the question, the method, the results, and the limitations, so a reader can follow and judge it. In peer review, independent experts check the claims before anything is published. We report the limitations and even results that did not work, rather than hiding them. Integrity is non-negotiable, no plagiarism, and no fabricated or cherry-picked numbers. And we weigh the societal impact, checking for bias, securing consent for data, and protecting people's privacy. Honest reporting and careful review are what keep the whole field trustworthy. Good method looks the same everywhere, even when the labs look very different. In Rwanda, a crop disease model is tested on photographs from farms it never saw in training, so the score reflects the real world. At a university lab in the United Kingdom, a team registers its hypothesis before running anything, so it cannot quietly change the goal afterward. On a benchmark leaderboard in the United States, a hidden test set ranks every model on exactly the same unseen data. The danger they all guard against is data leakage, where test examples slip into training and inflate the score dishonestly. The rule that unites every fair evaluation is the same: test only on data the model has truly never seen. A few traps turn a promising result into a mirage, so let's name them. First, data leakage, tuning on or even peeking at the test set, which secretly inflates your accuracy. Second, reporting a big number with no baseline. Without a reference, the number means nothing. Third, claiming victory from a single lucky run instead of averaging over several. Fourth, confusing statistical significance with a meaningful effect. A tiny gain can be significant yet useless. And fifth, leaving seeds and hyperparameters unreported so no one can repeat your work. Avoid these five and your findings will hold up to scrutiny. Let's gather the key ideas. Research follows a life cycle: question, review, hypothesis, experiment, analyze, communicate. A hypothesis must be specific and falsifiable. Split the data once, tune only on validation, and use the test set just once at the very end. Compare against a baseline, run ablations, and repeat over several seeds. A result should be both statistically significant and large enough to matter. And the goal throughout is work that is reproducible, honest, and ethically reported. Now let's check these ideas with 3 quick questions. Here's the first question. A team tunes its model on the test set and then reports that same test accuracy. What error is this? Once you tune on the test set, information leaks in and the score no longer reflects unseen data. This is data leakage and the reported accuracy is inflated. Question 2. You report that your new model reaches 88% accuracy. What must you compare it against for that claim to mean anything? On its own, 88% could be worse than a trivial model. You need a baseline, an honest reference, so the comparison shows what beating it really means. Last question, and it brings our ideas together. Model A beats Model B by only 0.1%, with a p-value of 0.001. Is this a strong result to publish? The tiny p-value shows the difference is real, not chance. But a 0.1% gain is too small to matter in practice. Statistically significant is not the same as meaningful, so this is a weak result. Wonderful work. You now know how AI research moves, from a sharp question and a falsifiable hypothesis, through a fair experiment to a significant and reproducible result. Compare against a baseline, guard against leakage, and report your method honestly. Do that, and you are no longer only using AI, you are contributing to it. I'll see you in your next module.